In this video, we will complete with the computation of vertical alignment. Now, how we can compute the length of the vertical alignment? Again, Transportation Engineering book and page here, page 71, okay, speaks about the vertical alignments. Now, as we said before, here we have the first type, which is known by the crest, and we have the second type, which is known by the sag. Our type is crest. Here we have the crest vertical alignment, okay? So the minimum length of the vertical alignment is given either by this equation or this equation. How to determine? Now it's as squared over 200 square root h1 plus square root h2 in square if s lower than or equal to L, or 2s minus 200 times square root of h1 plus square root of h2 in square divided on A when s greater than or equal to L. How to compute s and how to compute A? Starting with A at first, it's g1 minus g2 in the absolute value, and s is known by this side distance. So if the side distance, we have two types, either the stopping side distance or the passing side distance. Which one to compute we will see later. Now here for h1 and h2. So let's start one by one. First we have the computation of A equals g1 minus g2. g1 0.06 or 6% and g2 1.25%. So we take it as 6 minus 1.25 in the absolute value, it's 4.75. h1 and h2. h1 always 1.0 centimeter and h2 0.150 meter. Again, we get these values from here. Look, it says that if s is the stopping side distance, the height of the object is normally taken by 0.150 meter, which is now here h2, the height of the object, and for h1, the height of the eye, it says that height of eye is assumed to be 1.0 centimeter. So h1 is always taken as 1.0 centimeter and h2 is taken as 0.150 meter. Now after the computations of h1, h2 and A, we come to s. Now s is the stopping side distance, and s equal to, this is according to Turkish standard, dr plus dp. What's dr and what's dp? Dr, precipitation reaction distance. Dr is taken as dr times v. Now v is the design velocity, which is 70 km per hour, or the design speed. We have to take it into meter per second. So 70 times 1000 over 3600, it's 19.44 meter per second. For tr equals 2 seconds in Turkey. So always we take the value of tr as 2 seconds. This is according to Turkish standard. For dr equals to 2 times 19.44 and dr 38.88 meter. So this value must be the same for all the types of projects. It will be the same because tr is 2 seconds and v is 70 for all students. Then we come to the computation of dB, the braking distance. Okay, so dB is taken as, see here, v square over 2 times g times f plus minus g. Then, now g is the grade. We have actually two grades. Like, we have the first grade, which is G1, it's 0.0125, and we have the second grade, which is 0.06, right? So we take always G as the greater value in order to consider the most dangerous case, and we take it minus to consider the most dangerous case. Okay, so even our grade is positive, we take it minus. If our grade is negative, we take it negative. So again, here, what did we do? Okay, and V is 19.44 meter per second. We just computed, it's 70 kilometer per hour. And we have G, gravitational acceleration, it's 9.81. And F, what's F? Now F is the friction in between the tires and the road, F 0.31. We get this value from a table. Now here, our book, page 54, we have a table here. It's the coefficient of friction and stopping side distance. So we have the design speed here. Look, it's 70. According to our design speed 70, we have coefficient of friction 0.31. Okay, so we take this value. Then, as we said, we have dB equal 19.44 square over 2 times 9.81 times 0.31 minus 0.06. That means the braking distance equal to 77.05 meter. So the stopping distance equals to 38.88 plus 77.05 and equals to 115.93, considered as 116 meter or 115 meter. You can consider one of them. As we said here, look, S equal to dr plus dB, dr 38.88 meter and dB is here 77.05 meter. The sum of them will represent the stopping distance. Then we come again to the computation of L min. For the crest case, as we said, what we have L min equal one of these equations depending on S and L. So we start with the first one. We have the value of A computed, the value of S computed, H1 and H2 are known, and by this, just substituting in here, it's 4.75 times 115 square over 200 times under square root 1.070 plus under square root 0.15 in square, and L min is shown to be 155.39, approximately 155 meter. Now, is this answer correct, or we have to use the other equation? Again, we come here to the book. Look, now we computed this equation, right? And we have S lower than or equal to L. If this is correct, then that means this equation is used. Now for S, we have the stopping distance as 115 meter, and we have L 155 meter. Now L 155 is greater than S, which is 115 meter, then accepted. In case this is not correct, that means like L is lower than S. So again, we have to come to the second equation, compute the L min according to this equation. But in our case, L is greater than S, and this equation is correct. What do we have to do? After this, we have some important certifications for the obtained values, and this is named by the California standards, from where we can get it again from our book. It's let's see here. From our book, page 73. Here we have what's known by the California standards. California standard says that the minimum length of the vertical alignment must be 60 meters in case if the grade break is lower than 2 or design speed is lower than 60 km per hour. Now for the grade break, in our case, what do we have? We have 6, the first one, minus 1.25, it's 4.75. So this one, not satisfied. And VD is lower than 60 km per hour. In our case, we have 70 km per hour, not satisfied, so we have to not consider the first case. We come to the second. L min must equal to 2 times V if grade break is greater than 2, this is satisfied, and in case VD greater than 60, ours is 70, satisfied, so we have the minimum length must be 2 times 70 equal to 150 meters. Now, in our case, L, the length of the vertical alignment 155 meters, which is greater than 140 meters, 140 meters, so it's accepted, and we can consider any value from 140 meters and going up, 150, 155, 160, 165, whatever, but I just considered the minimum case, which is 140 meters. Then we come to the computations of the vertical curve. Now from section, which means this section, we have the height of intersection point is 757.5. Like from here, we just considered the height of this point actually. Then we have to compute the height of the beginning of the vertical curve and the height of the end of the vertical curve. How to compute it? Again, the intersection point and the BVC point are on the same tangent. So we just say that the height of this point equal to the height of this point, which is 757.5 minus the grade, which is 0.06 times 140 divided on 2. Okay, so 140 divided on 270 times minus 0.06. Why minus? Because BI point is greater in elevation than BVC, so we are going down. Take it minus, it will be seen as 753.3. so here it's 753.3. Now in order to set this point, again we have here 753, this is 754, so we have 753.3 will be somewhere in here. So this point is 753.3, and we take the intersection on the tangent as so this point here represents the PVC, which is the beginning of the vertical curve. Then by the same manner, we have to compute the height of EVC, the end of the vertical curve. Again, the height of the EVC starting from PI on the same tangent. Now this grade is, let's say it's 1.25%, and for the first grade, this one, G1, it's 6%. Okay. So again here, we start from this point, the height 757.5 plus, because we are going up, 0.0125 times 140 divided onto, it's on the height of 758.375 meter. So 758 is in here, 0.3, we take it the same here, it will be somewhere in here, then 75, somewhere in here actually, and we take it back to the tangent. So again, we take it back to the tangent. It will be somewhere here. Now we have the 70, so directly will be here. So this point is the end of the vertical curve, which is the end of the vertical curve. And this point is the start of the vertical curve. Again, we have 70 here. Okay, look, this is 70, and from here to here we have 70. As we said, the length of our vertical curve is 140 meter, 14 centimeter. Then okay, now what to do then? In order to compute these points, we have to use this equation that say y equal to YBVC plus g1 times x plus rx squared over 2. This equation gives the height of the vertical curve points. From where did we take this equation? Again, our book, page number here, page number 68, and this is the equation here. How to compute r? From here, g2 minus g1 over L, and g1 is known, y0 is known, which is the height of the first point. According to this, we come here. We have the value of YBVC is 753.3, G1 0.06, and R can be taken G2 minus G1 over L, 0.0125 minus 0.06 over 140, which is the length of the length of the vertical curve that we considered. Then we can say that r equal to minus 3.393 times 10 to the power minus 4. Substitute in this equation YPVC G1, r divided on 2 will be minus 1.696 times 10 to the power minus 4x squared. Now we apply this equation starting from the BVC coming to the EVC, and we can obtain all the heights of the vertical alignment. Connect them with each other, we obtain the vertical alignment. So in order to get these points, the easiest way is to form a table for the points. Now for the formation of this table, we have to consider what's known by stations on the road. Like the point of PVC starts here and the EVC will be in here. So we have to consider stations on these points. How to consider station? We have, for example, let's say that we start with the 0 station here, and for each 100 meter on the road we have a station. This is according to Turkish standard. Starting from the first station, let's say it's 1, then going 100 meters, second station will be 2, going 100 meters, third station 3, and like this. So we have to consider a station for the BVC, which is the beginning of the vertical curve, and I'll consider this station as 100. Like the name of the station, you can consider the 1, the 2, 3, 50, whatever, but I'll consider it as 100, the station number 100. Now here we have the beginning of the vertical curve will be somewhere in here. This is BVC, beginning of the vertical curve, and I considered 100 plus 0. I considered this station. Okay, so in here, like, we applied the table according to this. What I took the stations. I start from 100, this is PVC, and difference of 10 meters. Like each 10 meters I took a point, each 10 meters I took another point, and so on. Now the station here, just to understand the meaning of the station, if I consider this is the beginning of vertical curve point, and it's on the station as we said 100, and this is the end of the vertical curve. Okay, and it's on the station of now 101 plus 40. As we said, for each station, we have station here. As we said, for each station, we have 100-meter distance. Okay. Like this is station 1, this is station 2, if we said. So the distance between them is 100 meter. Okay. Now I took a station, or I took a point each 10 meters. Now I have here 100 meter. I took, as we said, a point each 10 meters. So I took the first point here. So the difference between these 2 points is 10 meter. So this point can be seen as 1 plus 10. Why 1 plus 10? Because the first station plus 10 meters. Same manner in here. Now I considered the BVC is on the station that's named by 100. So this is not distance. This is the number of the station. But this is a distance over the number of the station. So I took it on the station of 100. And I'm going 10 meters. So it would be station 100 plus 10 meters. Then station 100 plus 20 meters. Then station 100 plus 30 meters. Then station 100 plus 40 meters. Until station 100 plus 90 meters. We said that between two stations we have 100-meter distance. So when we came to 100 plus 90, then the next station will be, so it's 101 plus 0, 101 plus 10, and so on until 101 plus 40. So the distance from here to here, it will be starting from 0 coming to 100, and we have 40, so 140 meters. Okay, like just consider this one is the name of the station, and consider the distance is in here. Okay, so until we come from 0 to 100, so another station will be, so we start from 101. Just consider the name of the station here, the distance in here, and you will get them correctly. Then what did we do? Now here we have the grade, here we have the tangent. Actually, these computations for these two columns are not very important. We can directly get the profile elevation, but we can use them to be sure, or to make sure that we get these numbers correctly. Okay, starting first here. Again, this is tangent elevation. Take the height of the PVC, which is 753.30 plus 0.06 times 10. We obtain this value like this. Look. You just take it, the height of the PVC, which is 753.30, then plus we have 0.06, which is the grade, times alpha, and take the x in here. Okay, then take calc. I need it for 10 meters equals, gives you a number. This number, you just take it here. Then again equals for 20 meters equals, gives you number. Okay, 754.5. Again you take this number here, and so on until the intersection point. Here you have to start with the second grade. Now how to start with the second grade? Again, we start from this point, which is 757.5 plus, because we have increasing. Take it 0.0125 times alpha x. So this is your equation. And again, we have calc. Now here from 70 to 80, we have 10 meters. So 10 and 757.625, 757.625, and you get all of it. The offset values, for the offset values, this value represents the value of this, only this number, which is minus 1.696 times 10 to the power minus 4x squared. If we compute this alone, you can get the offset values in here, okay? As we say, these two columns, you can just pass from the station, the grade to the profile elevation without computing any of this, and you will stay on the correct side. Now, for the computations of this value, which is the profile elevation, we have, as we said before, to compute this equation. So just take this equation to the calculator. How? Again, 753.3, okay, plus 0.06 times alpha x minus 1.696 times 10 to the power minus 4 times alpha x in square. So this is your equation, and you consider calc starting from the first point. So starting from the first point, it's 10 meter, okay? So you have to compute this equation for starting from here. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Then 110, 120, 130, 140, okay? So starting from 10 equals 753.88. 753.88. Then again equals 20. 754.43. Okay, 754.43, and so on until we come to the last point, which is the end of the vertical curve. Now, the end of the vertical curve, as we saw, the height of it is 758.375 meters. So in the computation for this point, we have equals, it's 140 meters, right? Equals 140 meters and equals 758.375. So 758.375. This number in that equation must be similar to this number. If you get the same number, then you are working correct. Otherwise, you have to check if any mistake is done before, because this number must be the same as the height of the end vertical curve. Then, what to do now? After you obtained your numbers in here, these numbers are taken into the section. These numbers represents the profile elevation of the vertical curve. So, now starting 1 to 1. 753.30 the BVC. We took it in here. Then 753.88, but we're after 10 meters. So we have to divide the 10 meters first, and then we take the elevations. 10 meters, that means 1 centimeter on the plan. Now we come. The beginning of the vertical curve, it's on the height of 753.30. The next point, 753.88. Now this is the first point here, beginning of the vertical curve, and the next point will be in here. So this point must be on the height of 753.88. This is 753, and this is 754. 700, this one will be 700 53.8, but 0.88 it will be somewhere in here. This is our second point. So we can take them with the blue in order to distinguish these lines. The third one, according to these points that we get in here, we have to connect them with each other in order to get the vertical alignment. So starting from BVC point, this one, so this is the line of the road, the last one we drew in here, and goes in this manner. What we have here, we have the cut region, and the fill region will be in here. In order to show you the cut region and the fill region more obviously, we can use the colors. If we are going to represent the cut region, this is the road line, okay? This is the road line. So and the fill will be so. What we have to do first, according to this road, the line of the road, we have to cut this region in order to obtain the vertical alignment. Then this cut can be used here to fill this region in order to get the road line again. So this is our road in here. So by this, the vertical alignment is done, and in the next lecture we are going to speak about the super elevation.